Now we consider what happens if you put one of them solenoids in a circuit. Okay, this doesn't have to be a solenoid. It could be anything that we call an inductor, but let's think about what we mean by an inductor and what happens in this circuit. Let's just say you got this circuit, you got some resistance, that's inevitable, and you have a switch that you can close, and you got some source of EMF. Okay? Incidentally, when you get older, you kind of lose binary things. You know, at a young age, I got a little confused about which terminal, when you draw a source, is positive and which one's negative. And the way you want to think about it is the longer terminal pushes the current, okay? And that makes the longer terminal positive and the shorter terminal negative, okay? And I had that backwards, and I think I might have had that backwards in some of the other stuff I've done. So take that with a grain of salt. It's the kind of thing that I simply sometimes do, and can't seem to do much about it, and don't always notice it when I do. I need to be a little more skeptical. And I tell people to keep an eye on me, so you got to keep an eye on me. I had that wrong, people called me on it, so I corrected it. Okay, well anyhow, you throw this switch, and all of a sudden now you've got an electric field through here, and it's going to try to push current, right? Which means that the current should kind of instantaneously just appear, at least at the speed of light. You get a current in here because the electromagnetic field propagates very quickly. Not exactly at the speed of light in a wire, but you know, so quickly you don't notice it, but that doesn't happen. And the reason that doesn't happen is this coil. Well, what happens when you get a current through this coil? You get a magnetic field. We just saw how you get a magnetic field. Now, if you have a magnetic field, you multiply the magnetic field by the cross-sectional area, and you get the magnetic flux. But we know, at least if you've done the assignment and mastered the introductory problem set, that one of your basic laws of electromagnetism, it's one of Maxwell's equations essentially, says that when you change the flux, the magnetic flux, that induces an EMF opposite to the current, that tends to push current in the direction opposite to the current that's actually in the element that develops the flux. So again, we have a magnetic field inside the solenoid, and just mu naught times I times N. We have a magnetic field in the solenoid that gives you a flux that's clearly changing as the current tries to increase. Well, the current can't then increase too fast, because if it does, the rate of change of flux is too big. Okay, so you have an induced EMF that's equal to the negative derivative of your flux. Well, that induced EMF can't be bigger than the EMF of your source. Okay, you might think about why, but it's simply because the current just can't change that fast. We go through the differential equation, and that's what comes out. And there are more intuitive reasons, but we'll go with that. Okay, well, so this rate of change of flux, well, the magnetic flux depends on your current, because remember, the magnetic field is just proportional to your current. U naught times I times N. You know, you got I there. If I doubles, so does your magnetic field, etc. So this flux is proportional to the current, and the proportionality between, well, then the derivative of the flux is going to be proportional to the derivative of the current. And there's a proportionality constant that we call L, and that's called the inductance. Okay, so L is a proportionality constant for that particular solenoid or loop or whatever it happens to be. And that's called inductance. Now, many students are in differential equations, and we've already looked at the differential equation that governs this situation, and more generally, this situation. And we'll get to that, but not everybody's seen that, so we're not going to assume familiarity with the differential equation. But this should be clear. Okay, well now, the voltage drop from here, okay, if we go around the current, we go around the circuit in this direction, the voltage drop is in this direction, because the EMF is in this direction, which means this is at higher potential than this. So you drop potential as you go from here to here. So there's a voltage drop. So the voltage drop is equal and opposite to the induced voltage, the induced EMF. So that's the negative of the negative L di dt. It's just L di dt. And then you have a voltage drop IR across the resistor, and we're all familiar with that, I hope. And the voltage drop across your source in the direction from positive to negative. Well, the voltage drop across the source, the voltage rises as you go in this direction around the circuit, so you have a negative voltage drop. So what's our total voltage drop? Negative voltage of the source, the EMF of the source, and then you have a positive drop IR and a positive drop L di dt, this due to the resistor and the current, this due to the inductance element and the rate of change of the current. So now we have an equation. We can write L di dt plus IR equals the EMF of the source. And that equation governs everything that can happen with this circuit, assuming that it's an ideal circuit, the resistance doesn't change with temperature and other various things. You don't have any breakdown within the inductance or anything like that. Okay, so this is a simple equation. It's very easy to solve, and I'm going to go into the solution of that equation in the next clip.